Hello all, in this lesson we'll be discussing Le Chatelier's principle. Specifically, we'll be thinking about how changes in concentration, temperature, and pressure could affect the equilibrium, and lastly we'll talk specifically about catalysts. The homework for this lesson is continued from the last lesson. You should already have it written down, and our aim is how does Le Chatelier's principle apply to reactions? There's a quiz associated with this lesson, so make sure you are ready for that. All right, let's start with concentration changes. So we'll start by just thinking about what happens if I add more methane to the reaction. So the methane is this guy. So if I put in more and more and more methane, you're going to get a larger concentration of methane, and you're also going to be getting more collisions between the methane and the water. With that increased number of collisions between methane and water, you will be getting an increase in concentration for the hydrogen and also for the carbon monoxide. But this presents a conundrum. If you are increasing the rate of the forward reaction, you're making more and more hydrogen and carbon monoxide. And as their concentrations increase, you're going to notice more collisions between these two items. And as these two items collide, they're very likely to produce these two. So what's the effect on the rate of the reverse reaction as the concentration of the products increases? As the concentration of the products increases, the reverse reactions rate will increase as well. So eventually we'll reach a point where the reverse reactions rate is equal to the forward reactions rate, and then of course at that point we'll be at equilibrium. All right, let's consider the following equation. In this equation we have gaseous ammonia reacting with gaseous oxygen to produce nitrogen monoxide in gaseous form, gaseous water vapor, and also heat, which we're treating as a product. If you carry this reaction in reverse, it's heat, water, and nitrogen monoxide are colliding to create oxygen and ammonia. Both are valid. Now let's say, for instance, that we start by increasing the amount of ammonia. So the initial stress is to create more and more ammonia. So if I make more ammonia, then I'm going to be going through more collisions with oxygen, and you're going to see that the ammonia and the oxygen are colliding and creating these three guys. Now, as they're creating these three guys, these two both will experience a decrease in concentration. That happens together because they need each other to collide before they can create these three things. So you'll see a decrease in concentration for both of those, and of course, their concentration is decreasing because they're colliding and making these three things. So you're going to see an increase in concentration in the three products. So in that example, I was able to show that we had a decrease in concentration for these two items and an increase in concentration for these three items. There's got to be a way to simplify this, and that is where Le Chatelier's logic will come in. So Le Chatelier was a French chemist, and he said something really basic but very powerful. He said that reactions at equilibrium, like this one, will undergo changes to reduce stress. This actually sounds really similar to anything that any of the rest of us would do. If we're being stressed out, we'll undergo changes to reduce it. So in this case, in the initial case, the initial stress was that I added in some ammonia, and the reaction just underwent changes to reduce that stress. In other words, to take that increased amount of ammonia and turn it into a decrease. So let's apply Le Chatelier's logic to scenario number 2, where the initial stress is actually a decrease in the amount of ammonia. So Le Chatelier says that we will always undergo changes to reduce the stress. So the stress in this case is a reduction in ammonia. So what Le Chatelier wants is for the concentration of the ammonia to increase. There's only one way for that to occur, so check this out. It's going to be through the reverse reaction. When you take these three items and collide them together, you get these two items. So I'm going to take these three items and I'm going to see that their concentrations go down as they create more and more ammonia and oxygen. So I was true to my word there. I said concentration decreases in all three of these guys. So as their concentration decreases, the reverse reaction is going in full-fledged, and it's going to be creating extra ammonia and extra oxygen. We already predicted that you would be getting extra ammonia because of Le Chatelier's logic, but as a result, you'll also be getting extra oxygen. Now, here's a pattern that you may have already noticed. When you split the reaction down underneath its equilibrium sign, you'll notice a similarity between all the left-hand side things and all the right-hand side things. You'll notice that they have the same direction. So increase, 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 decrease, decrease, or increase, increase, decrease, decrease, decrease. And then lastly over here, Le Chatelier's logic says, when the concentration of a substance decreases, the reaction that produces that substance increases. Why? To reduce stress. That's always what Le Chatelier's logic would be, is to reduce stress and return to equilibrium. We can use Le Chatelier's logic for a closed system that has temperature changes as well. Examine this reaction where we have nitrogen gas colliding with hydrogen gas to create ammonia and heat. Now, especially if we can consider heat as an ingredient, this will make perfect sense. The reactants of the forward reaction are, of course, nitrogen and hydrogen. And the reactants for the reverse reaction are, of course, ammonia and heat. Now, heat is not typically a reactant, but in this case, we're treating it as one. So the reaction that's exothermic is going to be the one that releases heat, and that, of course, is the forward reaction. The endothermic reaction is the one that absorbs heat, which, of course, is the reverse reaction. So if we heat this system up, we're effectively increasing the concentration of the heat. That's what I'm going to be pointing towards for example number 1 down here. How will this shift the equilibrium to reduce the new stress? So the initial stress is an increase in heat. What Le Chatelier will need to do is to reduce that heat. And that's just because Le Chatelier will always undo whatever the initial stress is. But this will have effects over the entire reaction. For instance, the only way to really reduce the heat on the right-hand side is to use the heat. And the heat is either going to be used or produced in this reaction. If you go to the right, it's being produced. If you go to the left, it's being used. So that's exactly how I'm going to get rid of this heat, is I'm going to use it up as I go to the left. So you can't use heat without also using water and nitrogen monoxide. So I'm going to show that now by showing a decrease in concentration for the water and a decrease in concentration for the nitrogen monoxide. So you're going to get a decrease in the concentration of the heat, the water, and the nitrogen monoxide. But what you'll see in tandem with that is you'll see an increase in concentration for the ammonia and the oxygen. This is all just basic systematics. If you are using up this heat, you're using up all three, so they're all decreasing, but they're going to be producing those two things. This is what we mean when we say shift the reaction to the left. It's shifting towards the left-hand side where you get these two increases on the left, so it's shifting towards the left. So let's use Le Chatelier's logic to check out our next scenario. Let's say that the initial stress this time is the opposite, and I have decided to remove heat. Le Chatelier, of course, says that I must increase the concentration of the heat to undo this stress. Now remember, each one of these reactions either creates heat, like the right-hand side, or uses heat, like the left-hand side. So we're going to say that it's the forward reaction, which is going to shift into high gear and make more heat, which is our primary goal. In order to make all that extra heat, you're going to have to use the ammonia and the oxygen. You're going to have to use them up. So they're going to see a decrease in concentration. And as their concentrations decrease, you're going to notice that they're going to be colliding and making more nitrogen monoxide, water, and heat. So that means you're going to be getting an increased concentration of nitrogen monoxide, water, but also heat, which was sort of the original goal. And in this one, the reaction has shifted to the right. Now, pressure only affects the equilibrium of gases, but it does affect the equilibrium of gases. For instance, check out this scenario where you have a nitrogen and 3 hydrogen molecules. They could make ammonia molecules like this. If you're counting, we've got 2 nitrogens just like here, and we've got 6 hydrogens just like there. So it's the same number of atoms, but a different amount of space. And the reason why they might adopt this form over this form is because of the addition of pressure. So if somebody puts pressure on this, the molecules are going to shift to whichever format takes up the smaller amount of space. And that is a reaction to an increase in pressure. You guys do this naturally on the subway. If you guys get on the subway, you might notice that it's easier to take your backpack off because you're making a new arrangement that takes up less space. So what we would do, if the pressure on our friends and I increases, we'll take our backpacks off. So molecules aren't wearing backpacks. What molecules do is they adopt a more space-efficient appearance. Now in practicality, what does that really mean? It means that they're going to adopt whichever appearance has fewer moles of whatever. Check out this as an example. If I have nitrogen reacting with hydrogen to make ammonia and heat, make sure everything's a gas. So it's gas, gas, gas. Heat is neither, it's not FAs at all. But what I would point out is that you have in this equation 1 mole of nitrogen gas, 3 moles of hydrogen gas, in equilibrium with 2 moles of ammonia, and the heat doesn't count in terms of molecules. So what you've got is a 1 plus a 3, or a 4 moles, in equilibrium with a 2 mole appearance. So this is the side that would be favored if you have more space and less pressure, and this is the side that would be favored if you had extra pressure or less space. So yeah, let's go through that right now. So if I increase the pressure, it's going to shift towards the side that takes up the smallest amount of space. That is the right-hand side in this equation because it only has 2 moles. So that means you're going to see less nitrogen and less hydrogen, but you'll see more ammonia and more heat. If I decrease the pressure, it's going to shift to the side that takes up more space or more moles. So you're going to see less ammonia and less heat, and you're going to see more hydrogen and more nitrogen. Now, if both sides of the reaction had an equal number of moles, then you would not see the reaction shift at all. And because an increase in pressure is usually accompanied by a decrease in volume, you would notice that the concentration of everything increases equally. So you really don't see any shift in equilibrium at all, but everything's concentration increases proportionally to its volume. So for catalysts, you guys need to know that a catalyst functions by increasing the effectiveness of collisions, thereby lowering the amount of activation energy which is actually needed for the reaction to occur. So if I were going to expect a catalyst to work on this reaction, you would see the following. You would see an alternate reaction pathway appear with lower activation energy. So how would this affect the forward reaction? Of course, it would speed it up. How would that affect the reverse reaction? Also, it would speed it up. The lower the activation energy, the better for both reactions. So that means that they would both speed up equally, and you would not see the equilibrium shift. And although you would not see an equilibrium shift in the reaction, you might find that equilibrium comes faster. And with that, we've reached our pair up. Please copy down the questions and the equations. So maybe what's highlighted. And you can leave the answer choices off. We'll do those in class. Here's your summary. Copy down this grand table, which we will work on in class tomorrow. Thank you for watching.